Last video of the unit, guys. And today we're going to finish things out with groundwater and how water moves through our ground and the soil and the rock. And one of the main terms that you'll need to understand for movement of groundwater is porosity. And porosity is the amount of pore space, the amount of empty space in a rock or soil where this water can actually fit or be stored. And it's usually measured in a percentage. And you can see in this picture here, these are pore spaces, and water fits in between them. Even in solid rock, there are many rocks that are permeable that allow water to flow through them, like sandstone, for instance. Some rocks don't allow water to flow through them, like granite, a solid piece of granite. And you'll see that if pores get filled up by other things, it reduces the amount of space where the water can fit, because other things are fitting in there, like little rocks. So porosity depends on three factors. And the first is shape. And it turns out that the rounder the sediment, the greater the porosity. And that's because round sediments don't fit together very well. They're not like jigsaw puzzle pieces. And soils made from these things, these round, highly spherical, well-rounded sediments, would have lots of space between them, whereas soils made from sediments that are angular and not very spherical, they start to fit together and lock in to those empty spaces with actual rock and fill up the space that would have been taken up by water with rock or with sediments. So just remember, the rounder the sediments, the greater the pore space. Okay, second factor, packing. Just like those potato chips or the box of cereal that you get from the store. It looks like there's this huge bag, but as the thing's going down the road in the truck on the way to the grocery store, all those pieces are getting sorted and packed. And as they get packed, they don't have as much space between them. And you can obviously see that in this picture. On the left-hand side, you got all kinds of space. They're not packed together very tightly. Compared to the picture here on the right, a lot less pore space because they're packed together in a different manner and much tighter because of that. So if you compact a soil, it doesn't hold as much water. It also doesn't drain as well, too. And that can happen from all kinds of things, like cars driving over, unpaved areas and squishing the soil down. Okay, third factor, sorting. Soils that are well sorted, that means they have the same size and shape, have more pore space between them than soils that are poorly sorted or unsorted. And you can see that in the pictures here. On the right-hand side, you'll see, hold on, a little screw up here. You'll see this is a relatively well-sorted soil. Lots of space between them. The particles are round and they're not the same size, but they're close. And so there's not a lot of little pieces filling in. Whereas the bottom picture shows those same big and medium-sized ones, but a lot of small ones are filling in the empty gaps. So this is not as well sorted. And you want to think of sorting like, if your parents ever asked you to sort a bunch of coins. You have to put the quarters with the quarters, the dimes with the dimes, the nickels with the nickels, the pennies with the pennies. And then you can roll them up and bring them to the bank. That's sorting. In this case, soils are sorted or poorly sorted. Remember glaciers. Remember back to the Unit 4 when we learned about glacial till. And that's kind of like this picture here. Glacial till, remember the glaciers drop all different kinds of sizes and shaped rocks just in a haphazard, random way. And so these soils are poorly sorted. And you'll see that, in the Adirondacks, there's areas that have glacial till and there's poorly sorted soils, a lot of swampy areas. So that does have an effect on groundwater. Okay, here's another close-up showing porosity. Round sorted, loosely packed soils have the highest porosities. And you can see the unsorted on the right versus the sorted on the left. So let's graph these relationships. First one, as the soil gets rounder or more round, the pore space, something's going to happen to it. Remember, rounder doesn't fit together well, so there's more empty space between them. Graph goes up. Direct relationship. Okay, packing. The more packed. So the more you pack the soil down, let's draw an arrow instead of a circle there. The more you pack that soil down, the less the pore space. So it's an inverse relationship. And lastly, the more sorted the soil gets, remember, more all the same size and shape versus unsorted where there's little tiny ones mixed in there. So the more sorted it is, the more pore space. So these are graphs that you should be able to do, and that if you can answer these graphs correctly, it tells me that you understand the relationships between these factors and how to draw a graph. Okay, there's a little side note here I think that's interesting. If you have a bunch of sediments that are different sizes but all round, all the same shape, in this case round, they will have equal porosities regardless of their size. Now I know this is not an ideal situation. In real life, sediments aren't like these spheres. But it is interesting to note that they, in this case, they all have 48% porosity. And the reason why is you have lots of little pores here, medium amount of medium-sized pores here. You know, if you added them all up, there's a medium amount of medium size. Here there's a lot of really tiny ones. And the last one, you have a few amount of really big pores. And if you do this mathematically, which I could do it on the board, although I'm not going to spend the time today, you got to trust me on this. If you do the mathematics of this, you'll find that the empty spaces between these spheres where the water can exist is all the same. And so there's 48% that could be water and 52% that's actually particles. But it only occurs if it's round or spherical and not some other shape. All equal. Okay, some more properties of groundwater. Permeability, the ability of water to soak in, or the rate at which water soaks into the ground. And samples with large spaces will be more permeable than samples with smaller pore spaces. By more permeable, it means the water soaks in faster. And it's easier to soak through these large pore spaces. There's less things getting in the way that the water has to go around. So large connected pore spaces allow water to flow really well through them. That's why, you see a lot of areas that are poorly drained. They can modify that by digging up that area, like around a foundation of a house, for instance, and putting in gravel, large pieces of like limestone gravel or other kinds of gravel, and that allows the water to soak really quickly through that area and away from the foundation of a house. So if you look on the, let's go back one here. If you look on the grain size section on your reference tables, in this chart on the left, this is just taken right out of your reference tables. Pebbles, cobbles, and or boulders, things like conglomerate and breccia might have a more permeable nature, or sandstone, more permeable than a siltstone or shale where the particles are much, much smaller. It's harder for the water to get through those smaller particles and around them than it is the larger ones. So what that means for you guys is some areas have naturally occurring rock that's just less permeable than other areas. And so there's poor drainage in those particular areas because of that. A lot of wet basements. All right, this slide just quick shows that large, round, sorted particles have high permeabilities. And you can see different examples here. We have a crystalline igneous rock. It's not going to allow water to really go through it. That's pretty much impermeable. Clay-rich layer, there's so many small pores here, it's hard for water to get through it. A lot of times it'll hit a layer of a clay-rich layer or even shale and flow sideways out the edges. Quartz sandstone, this has a high porosity and high permeability. So it allows water to flow through quite easily. Lots of pore space and it's open. And glacial till, low porosity, low permeability. Remember, all the spaces are filled in by the little particles too that the glaciers have dropped, as well as the big ones. And so there's not a lot of pore space, and even though they're connected, the pores are connected, the water has a hard time getting around all these little particles. So poorly drained glacial soils, that's typical. Just summing this up, almost no permeability in the first one. Second picture, lots of pore space, but it's not connected. Third one, low pore space, slows the water down, doesn't drain fast. And the last one, water flows through easily through the quartz sandstone. Okay, so hopefully you guys understand permeability, the ability of water to flow through the rock. Okay, note, soils that allow water to infiltrate downwards are called permeable soils. And you've heard me mention this term already. So permeable soils. And why are New York State soils in New York State impermeable during the winter months? Winter months, but not summer months. If you guessed that the soils are frozen, you're right. So frozen soils don't allow water to flow through them at all, or very little, because those pore spaces are now all frozen up. They're connected by frost. Now, sand and gravel, which one is more permeable than clay? Or are they more or less permeable than clay, I should say? And sand and gravel are much larger than clay, so they should be more permeable than clay. So these are just, typical questions you might see. Okay, third property of groundwater, capillarity. Just like the capillaries in your body, or capillary action by plants, capillarity is the ability of water to be pulled or flow upwards in rock or soil against the pull of gravity. And you can see in this picture over here how the water is moving up. And the reason why it does that is because water likes to stick to itself. It's very cohesive. And water likes to stick to the glass. It's very adhesive. So water has these properties where it likes to pull itself up against gravity. Mercury, on the other hand, has the opposite kind of effect. It doesn't like to stick to the glass, and it's kind of heavy too. But water has lots of capillary action where it's pulled up. You can see this if you stick a napkin or paper towel in a glass of water and watch the water get pulled up. So why is that important? Well, plants need that. Roots need that to grow, to get water, for their photosynthesis. And so soils that have smaller particles allow the water to stick to them easier by these two properties, adhesion and cohesion, and be pulled higher upwards. And so the most capillarity would occur in the clay. The least would be in the sand because the particles are bigger. And kind of a medium effect with loam, which is kind of a mixture of the two. So when pore spaces are connected and very small, that's when capillarity is highest. Connected and very small. Now if it's too small, like this clay can actually be really small sometimes, then it actually has lower capillarities because although it's connected, it's just not well connected. There's too much plugging up the space. So which rock would have the highest capillarity, ability to hold on to water the most? And I would argue that these rocks down here would probably have the most capillarity. I would even say probably siltstone over shale, just because shale can be impermeable in some cases. But conglomerate and breccia wouldn't have much at all. Particles are too big. The capillary fringe, a happy place for tree roots. So you can see how the roots of a tree, they're in this unsaturated zone. Unsaturated meaning it's not completely filled with water. There's some water stuck to the edges of the soil particles by adhesion and cohesion. And the roots are down there. They're getting their moisture. But it's not in the area. The roots aren't in the area where it's completely saturated, because that would rot the roots out where the water's filling in those gaps completely. And the capillary fringe is the area just above the water table. This is the water table right here, where moisture is being pulled upwards by capillary action, by that adhesion and cohesion. And the roots go right down, like the taproot of a tree might go right down to that level to grab its moisture. All right, correctly filling these graphs in your note packet. Well, you guys, you may or may not have this depending on which class you're in, but let's try it. Particle size versus permeability rate. So remember, as the particles get bigger, it's easier for the water to flow through them. So the permeability rate is going to go up. Particle size versus capillarity. As the particles get bigger, remember, the bigger, the worse the capillarity. Capillarity needs small pieces for it to be well, to work well. So this would be the opposite. And there we go, just checking the answers. Okay, we already went through this. Some new terms, zone of aeration. It's where the air exists between some of the particles. Zone of saturation is where it's completely filled between the rock particles. And the water table, I already mentioned right there, and the capillary fringe. How much do we depend on groundwater? According to the USGS, 22% of all fresh water withdrawals is groundwater. So that's quite a bit, but not a heck of a lot compared to the other 78%. 37% is for agricultural use, mostly irrigation. So we're pumping a lot of this groundwater out of the ground and putting it on plants. Got to treat it right. 37% of the public water supply withdrawals. 51% of all drinking water for the total population comes from groundwater. And 99% of drinking water for the rural population. Yes, around here, a lot of us have wells. So we have to not change our oil and dump the oil in the ground in our yard because that's going to end up polluting our well and maybe a bunch of other neighbors' wells too. I forgot what the number was, like 1 gallon of oil dumped in the ground pollutes like 10,000 gallons of drinking water. It's some ridiculous number, so you have to be careful. Top 10 water do's and don'ts. Remember, disposing of chemicals properly. If in doubt, just call your local village or town office. Use motor oil, 5 gallons a day. Any place that changes oil by law, at least in New York State, has to accept 5 gallons of used oil a day, which is more than any of us are going to produce. Limit the amount of fertilizer on plants. Don't over-fertilize. Take short showers. Shut water off while brushing teeth. Run full loads of dishes and laundry. Don't do like partial loads. Check for leaky faucets or toilets. Water plants only when necessary, or try to capture rainwater off your roof and use that to water plants. Keep a pitcher of drinking water in the fridge and get involved in water education, which you're doing right now. And you can see people changing their oil on the side of the road, dumping the oil. Can't do that. And that is it, guys. See you next unit.